So let me introduce my friend and colleague, Dr. Rashmi Roy, who has obtained her PhD degree in 2015 from IIT Kanpur under the supervision of Professor Y.D. Vankar. Her PhD work was based on the synthesis of glycosidase inhibitors and gold catalyzed glycosylations. After receiving PhD, she was interested in space research. She joined the Department of Mechanical Engineering, IIT Kanpur, in an ISRO-funded microgravity project as a senior project associate. Then she moved for another postdoctoral fellowship in the University of Alberta, Canada, where she worked on complex glycolipids. She worked for a while in GVK Bio Hyderabad and then moved to TCG Life Sciences, Kolkata as a research scientist. She joined Madhya Pradesh Institute of Technology and Science as an assistant professor and since April 2024. She has published papers in notable journals like Analytical Chemistry, EJOC, OBC, RS Advances, etc. Her research work is mainly based on the organic methodology development, synthesis of a novel glycoconjugate and a molecular modeling study and simulating reaction mechanism. Madam Rashmi Roy, madam, I welcome you to start.
Yes, am I audible?
Yes, ma'am.
Am I audible?
Yes.
Okay.
You can
yeah. So today my topic of this presentation, first of all, I thank all my colleagues and all participants, everyone, and I am especially thankful to CAME Convergence 2025 team to invite me to give a presentation regarding my research work. Okay, so whatever the work today I will discuss, that is only done in my PhD and postdoc tenures with Professor Y.D. Vankar and Professor Todd Lowry. Okay, so today my topic of discussion is strategic synthesis of neoglycolipids and iminosugars. So first I will discuss about the synthesis of neoglycolipids and what are their importance and why we are about to do so. And in next part I will discuss about the importance and synthesis of iminosugars. So first, I am coming to the topic that what are these glycosphingolipids and neoglycolipids. So both are glycolipids only, but thing is that glycosphingolipids are naturally occurring glycolipids, whereas neoglycolipids are non-natural glycolipids, and these are mainly artificially synthesized. And so what are glycosphingolipids? Glycosphingolipids are glycolipids only. As the name suggests, it contains one sugar, one polysaccharide in it. Like here, it is shown here in the left part of this molecule. This is a representative glycosphingolipid, and it is connected with ceramide moiety. Ceramide is nothing but a protein, ceramide is nothing but a fat, and that is more abundant in skin, and it is responsible for the texture of skin, of our skin. So lot of ceramides are present in animal skins, and this is the representative chemical structure of glycosphingolipids, LCGG4. And glycosphingolipids are not only involved in...
I cannot see your slides. I think you have to share the slides. Probably it is not seen.
Okay. I have shared.
Actually, I cannot see. Others maybe, I don't know.
Is it visible? Sir, they are telling
yes,
that slides are
visible.
Oh,
yes, visible.
Okay, yeah. I will rejoin then maybe.
Should I rejoin again?
No, I will rejoin. You continue.
Okay, sir. Yeah. So I was discussing about what are these glycosphingolipids. These are very interesting molecules, and as the name suggests, it contains one glycan part and a lipid part. So this glycan part is consists of polysaccharides. It may be disaccharide, trisaccharide, tetrasaccharide, and so on. And this our lipid part is consists of long alkane chain, and specifically, glycosphingolipid must contain amino alcohol sphingosine. That is the structure of amino alcohol sphingosine is shown here, and in our example, it is our glycosphingolipid is LGGD4 that consists of this glycan tetrasaccharide, and in lipid part it is a ceramide. Uh, and here, how this molecule interact with cell membrane, that is shown here. Now, cell membrane, we are coming to the topic cell membrane. Cell membranes are consist of protein, lipid, protein, and our glycosphingolipids are incorporated in that cell membrane, and this structure is shown here. If we consider this as protein, lipid, and protein part, and glycosphingolipids are inserted there, and so lots of interactions are taking place between this cell membrane and glycosphingolipids, and these are very important. And the glycosphingolipids not only, and they are responsible for a myriad of biological cell recognitions and many other kind of biological activities. And not only that, they can act as tumor associated antigens also. For example, this LGGG4 is a leukemia associated GSL antigen as well. Now, this thing is that a wide variety of normal and pathophysical processes involves interaction between glycan binding proteins and glycosphingolipids, and they are responsible for important biological roles. Now, problem is that it is very difficult to isolate these glycosphingolipids from animal sources in pure form. So, due to this reason, the study of protein and GSL, glycal binding protein and GSL interactions cannot be done so far so widely in past decades, and so this is an emerging area right now. So, what people are doing nowadays is that they are synthesizing artificially glycolipid moieties, and they are going for this protein and glycolipid interaction studies. Now, in our work, we made these artificial glycosphingolipids. Those are known as the neoglycolipids, since they are artificially synthesized. And we wanted to know that these artificially synthesized new glycolipids, can they act as a glycosphingolipid surrogate to study that glycal binding protein and glycosphingolipid interactions or not. That was our aim of this research. And understanding the mechanism of this GBP-GSL interactions process may lead to the development of new infective, anti-cancer, and anti-inflammatory strategies. That is why in 2020, 5 of the top 10 selling drugs are glycosylated and have a combined revenue of 58 billion US dollar. And the global market for glycomics drugs are about to reach 257 billion USD by 2028. So this is the importance of our glycosphingolipids and neoglycolipids. So here, how these glycosphingolipids are binding to the protein in an artificial environment, that is shown here. If we consider this is our protein and this is our what we do generally, that is not part of my research. That was done by our research collaborator, Professor Klassin group. What they did is that they take nanoparticles as nanodiscs, and there they insert these glycolipids first, and after that they study these protein binding interactions with this nanodisc and glycolipid combined in this nanodisc structure. So this is one example where it is shown how this nanodisk recruitment mechanism takes place in this artificial environment. So to study further, so that this neoglycolipids can really can act as the glycosphingolipid surrogates or not, we have planned to synthesize 9 neoglycolipids. So we have planned this disaccharide 1, tetrasaccharide 2, this tetrasaccharide 3, 4, 5, 6, and 7, 8, 9. Okay. So these are very complicated structures, and you know that requires a lot of time. But here we have followed one simple strategy to synthesize these glycosphingolipids or neoglycolipids, whatever you would say. So thing is that we have first synthesized this disaccharide, and to synthesize other polysaccharides, I am showing you. Yeah. We utilized these compounds, azides 10, 22, A2H, these azides. Now, these are actually tetrasaccharide to pentasaccharide molecules we have already had with us that has CH2 azide group in its anomeric center. That is known as SP. SP group means CH2 azide group. Now, from these intermediates, we have synthesized the other neoglycolipids. Now, we are coming to the synthetic strategy. First, I have synthesized the lipid moiety started from glycerol. So, first, glycerol was protected using benzaldehyde, and there are two possibilities in this protection step. It can bind from this diol side, since there are three triols in this molecule, and two of them are symmetrical and another is unsymmetrical. So there are two kinds of possibility to form this benzaldehyde protected hemiacetals. Now from the mixture, we have isolated the desired one, this 10. After that, we have deprotected this acetal group, and we have introduced long chain using sodium hydride and this alkane bromide in presence of DMF at 0 degree to room temperature to find this long chain compound. And while doing this, doing so, we have actually faced a lot of solubility problem associated with this molecule. This molecule is not soluble in methanol due to presence of long chains, and we are supposed to do this debenzylation in hydrogen environment, and so for that purpose, what we did, we mixed it with a little bit of DCM, and we took DCM methanol mixture in 1:3 ratio to form this molecule 13. Now 13, the free OH group was 13 was replaced by this acid group following these under these reaction conditions. First, we tried this sodium hydroxide THF in presence of potassium iodide, and the reaction did not work. Then we take THF DMF in 3:1 ratio. That time also reaction didn't work. So I have combined these two reaction conditions together and applied here. I took sodium hydride in presence of Ki in THF DMF medium 3:1 to got this molecule 15. And this compound 15, that is a lipid molecule that is not stable in column. So we had to take care that column should be done very quickly. Even the TLC reference also used to decompose in room temperature, and TLC also came like a stick, means the compound was not stable. And so what could be the results of this instability factor? To know this, we have just predicted that maybe it is forming a an intramolecular hydrogen bond like this fashion, and making this CO bond very labile, and so that in room temperature itself, this group is living from the compound is decomposing like shown in this scheme. So this intramolecular hydrogen bonding may be the reason to destabilize this molecule. So what I did, I just mixed the compound with some toluene and kept in freezer. But that also I did not find much development. The compound used to decompose within 1 or 2 days. So to prevent this one, we just propose that maybe reactions with N-hydroxysuccinamide with this lipid free acidic group maybe will maybe a potential solution. So because here this free H group will not be there, and the intramolecular hydrogen bonding will be prevented if we substitute the molecule simply by this with the succinamide group. So that was our proposal, and it worked. So after doing this coupling with N-hydroxysuccinamide, we could keep the compound for at least 1 month. Like that, compound was stable. So we did not do any column further, just kept it, did workup and used directly for the yeah, for the next step. For next step. Now we had many polysaccharide molecules having CH2, CH2, N3 group in anomeric position. So that is what is known as SP group. Now the problem associated with this methodology is that we had these intermediates, all these azide intermediates is 1 milligram. So from this 1 milligram, I had to do at least 2 to 3 steps to move to get the final molecules, along with the column chromatography and characterization of the molecule. So this was very tricky. So this 1 milligram compound, first this azide group, I just reduced it under hydrogenation condition to get this amine intermediate, and then I reacted them with this form in hydroxysuccinamide ester 16 in presence of NMP room temperature, and it took around 1 or 2 days to got the final product. Now the problem is that I was unable to check TLC also frequently to monitor the reaction, because you see, after having 1 milligram compound, first I have already reduced the azide group to free amine group. So first step is done. I filtered it through Celite and collected the compound, and then I am going for the next step. So after this also again I am losing my compound. So in the final step, I did not used to monitor, used to do TLC also. I directly used to take the sample for LCMS and used to take mass. So that is how we made these compounds from started from azide groups to our neoglycolipid molecules. Now, uh, along with these tetrasaccharide and pentasaccharides, we have made one disaccharide also that was typically synthesized in the lab. So I started from lactose, and first I did glycosylation in the anomeric position under standard condition. This is a well-known condition using BF3 ether to form this SP group, to introduce this SP group in the anomeric position. And then I just reprotect the acetate groups under sodium methoxide methanol condition and pass them through amber list column. And then as usual, I move forward by reducing this azide group using hydrogen in palladium carbon to form the free amine. And finally, I coupled it with 16, compound 16 under standard condition to get my final compound. Now, the purification of these neoglycolipids are another headache. Really, it is an headache, because I had only 1 or 2 milligram, 1 milligram of sample, and I have to purify to get at least one good proton. So how we did it, and you see, if we look to the structure of these molecules, there are you see how many weight groups are there in this tetrasaccharide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 13 free weight groups are associated with it, along with a long lipid chain in this, yeah. And the free amine group is also present. So you can imagine how much polar would be the molecule. So normal column never will work to purify these molecules. So what we did is that we did iotropit column. It is a material just used for column chromatography for complicated glycolipids for the purification of mainly suitably for glycolipids and complex polysaccharide units. So in iotropit column, you can also do column in methanol medium also. While normal silica gel will dissolve beyond 20% methanol in DCM medium. If you go beyond 20% methanol in DCM medium, normal silica gel column will dissolve in it. But iotropit column can bear up to 100% methanol injection through it. So what I did is that I did very small column you have to make for this purification of 1 milligram sample, because we started from 1 milligram and we're going to another 2 step, your compound is less than 0.5 milligram or like that. So very small column you have to make for this purpose, and you load it with iotropit and start with, I started the column with 100% DCM. First, pass 100% DCM in the column, then inject your sample dissolved in methanol. Then gradually we have to increase the polarity of the polarity of the solution, like 10% methanol to 100% methanol. And when I purified disaccharide, it came around 20% methanol in DCM system. But while I purified tetrasaccharide, it is going around 50% DCM methanol system. And finally, when I purified these compounds, especially I'm showing the structures. Yeah, these kinds of molecules which are containing in new, along with our glucose, galactose, and neurominic acid moieties, and they are basically pentasaccharides. They used to come in 100% methanol only. Just when your DCM concentration is low, your impurities will come out, and finally the final molecule will come at the 100% your methanol system. So that is how we did it. And also column, after doing column, you are unable to check the TLC. Because you don't have much sample. Doing TLC is just means that you are just wasting your sample. So how to do it? I used to collect 10 fractions. So so I assume that first I did with disaccharide, and I came to know that in 20% methanol and DCM, my compound came that time, because it is synthesized in the lab, and I had sufficient compound to work with. So what I did, I came to know the polarity of the molecule. So when we are going for tetrasaccharide or pentasaccharide, at that time I have collected fractions beyond 30% methanol in DCM, and I collected almost all the fractions for NMR study. And when I saw the peak, I went for Maldi study, and when Maldi also was positive, that fraction I submitted for LCMS. And how to take NMR for this less than 1 milligram sample? Normal NMR tube will not work. In that time, you have to use Shigemi NMR tubes, where you have to maybe the tube is designed in such a manner that half of the tube is already injected with some material, okay, some solid material. Above them, you have to just put 2-3 drops of your sample where your compound is there, maybe 0.5 ml. or less than 0.5 ml of sample you put in that tube, and you will be able to get NMR of that sample for when you have very less amount of sample. So by this way, we have detected the compounds, and finally, whatever we have planned, all the compounds we were unable to synthesize. I have synthesized this disaccharide, this tetrasaccharide, and these two pentasaccharides. Those work well, and other things we were not impressed with the NMR, whatever we got. So those things we just discarded. So after planning 9 molecules, we were able to get 4 molecules out of this among all those planned neoglycolipids. And after that, we send the molecules for further study in our collaborators. So what they have studied these neoglycolipids in their standard methods using catch and release ESI mass spectroscopic techniques. They have injected the compounds in nanodisk, and this glycosphingolipid and protein bindings interactions they have studied, and they have proved that these neoglycolipids are suitable enough for the study of glycosphingolipid protein binding interactions. So they could be substituted instead of natural glycosphingolipids. So that is why, because naturally glycosphingolipids are difficult to get in pure form. So we have to develop methods so that artificial glycolipids could they work in place of glycosphingolipid to finding out these protein and glycolipid interactions. That is what the paper was published in 2020, and that is the end of our talk of my first section. And in my second section, I have less amount of time, so I have to move first. So in the second chapter, I will discuss about the synthesis of iminosugars. So iminosugars are known as good glycosidase inhibitors, and this is my PhD works, one portion of my PhD works. So these are good glycosidase inhibitors. Now, what is this glycosidases? Glycosidases are the enzymes which are responsible for the uh, means removal for the cleavage of glycosidic bonds in our body system. So in our body system, where when we are consuming complex carbohydrate as food, okay, in our food percentage, 60% is we are consuming as carbohydrates. Now, what is happening to this carbohydrate? So carbohydrate molecules contains glycosidic links in anomeric center, and our glycosidase enzymes are responsible to cleavage of this uh, uh, anomeric glycosidic bonds. Alpha glycosidase enzymes are specific to cleave alpha glycosidase bond, and beta glycosidases are responsible to cleave the beta glycosidic bonds. And by this way, what they are generating is that in our body system, they are generating lot of monosaccharides, that means sugars. Malfunction of these glycosidase inhibitors are responsible for various kind of diseases. Number one is diabetes. So it is very important to develop glycosidase inhibitors to combat diabetes, because diabetes is a means everyone knows in our country how much people are suffering from diabetes in every family. If you look forward, if you look the old people, almost everyone has diabetes. And so that is why it is very important to develop new glycosidase inhibitors as anti-diabetic agents. So these are some iminosugars. Iminosugars are nothing but they are in in sugar molecule, we have one oxygen ring in glucose that everyone knows. When we are substituting this glucose with a nitrogen atom, that could be considered as an iminosugars. And what is the when we are administered these iminosugars in our body, what is happening? Our glycosidase enzymes. Okay, we are basically trying to fool these glycosidase enzymes. What they are thinking that okay, this is our sugar molecule, they will bind with the glycosidase inhibitors, and the enzyme will be locked inside the body system. So this is the concept to develop uh, anti-diabetic drugs in one way. So these are the examples of representative immunosugars like nozerimycin, phagomin, deoxynozerimycin, miglustat, miglitol. Miglustat, trade name of miglustat is Javesca, and this is a medicine for Gaucher disease and type 1 Gaucher disease, and miglitol is an example of type 2 diabetes. So that is why we have also planned to synthesize a series of immunosugars, and we wanted to study that are they good inhibitor of glycosidases, and if they are good inhibitor also, are they is it inhibition is taking place from alpha side or beta side? That is also one concern. So these molecules should be very specific, that they will inhibit alpha glucosidases or galactosidases, or beta glucosidases, or whatever it is. Okay, so glycosidase enzymes are two times, alpha and beta. So like alpha glycosidases, like alpha glucosidases, alpha galactosidases, these are the examples of alpha glycosidase enzymes. And similarly, we have beta glycosidase enzymes, and they are very specific towards the reaction, that they will cleave the alpha bond or beta bond in this polysaccharide unit. So we have planned to synthesize these immunosugars. I am showing you the chart. Okay, so how we develop? We have developed a common reaction scheme, so that following that scheme from an intermediate molecule, we can synthesize a library of immunosugar. So for that purpose, we started from D-mannitol, and we have protected with acetone the free hydroxy groups, and then one terminal hemiacetal moiety was cleaved using this concentrate HCl in ethanol medium, followed by sodium periodate to get this corresponding aldehyde. Now it was subjected to Henry reaction to get this nitro compound, and finally treatment with methyl chloride in triethylamine, it gives this vinyl nitro compound 1. Now this is subjected to Grignard reaction to incorporate one allyl chain here, and after that I have reduced this nitro group to the corresponding amine group, and followed by CVZ protection gave this one. And after that I have clipped the other terminal, this hemiacetal group, to get this free diol, and then I clipped it with sodium periodate, and to get the corresponding aldehyde, of course. And finally I reduced it using sodium borohydride to get the free OH. Now I methylated it, and finally this treatment with this tertiary butoxide gave this closed this ring closed products, these two diastereomers. In this stage, we have separated the diastereomers in column chromatography. They are stable enough, and after that, I have followed just normal deprotections. First deprotection of CVZ groups, and then deprotection of this hemiacetal gives this compound 2. This is one example of immunosugar, and also I have did this. Reductive amination in this free amine group to incorporate a butyl chain here to get the other group 3. So similar treatment with the other diastereomer gave compound 4 and 5. And in this stage, I have proved the stereochemistry here. First, I did COSY. I took COSY NMR and found out what is this H3 hydrogen. And after that, I went for NOE study. I irradiated this, when we irradiated this H3 hydrogen, we found for this compound 8, we found that enhancement of peak of this H5 and H2. So these 3 hydrogens are cis. And a similar NOH study proved that these 2 hydrogens are trans in 9. So stereochemistry also proved there. And from this the major diastereomer, which we have separated, I did further treatments with this free double bond. I have dihydroxylated using osmium tetroxide, followed by sodium periodate treatment and sodium borohydride reduction gave these 2 products. Again, this CBZ reductions in standard hydrogenation condition give this iminosugar 6, and after that I did again reductive amination to incorporate a butyl group there. So by this way, I have synthesized from compound 2 to 7. Now, compound 9 and 10, we have actually started from this synthon 8. This is another vinyl nitro compound started from D-mannitol using a different methodology. That was also developed in our lab itself, this synthon. And from there, following similar kind of reaction pathway, I got 9, 10, and 11, these 3 molecules. So total 10 molecules we have synthesized, and these compounds were sent for further glycosidase inhibitor study. And finally, we found that compound 4 is a good inhibitor of alpha galactosidase from coffee beans, and it has 0.85 millimolar. It is showing IC50 values around 0.85 millimolar. And this same compound is a good inhibitor of alpha glucosidase from rice. It has we got 0.25 millimolar inhibition from there. So basically, this compound is a good inhibitor of alpha glycosidase inhibitor. This is good for alpha, means it is showing inhibition towards alpha galactosidase or glucosidase. And compound 4, this is a good inhibitor of beta mannosidases. So it is good for beta glycosidases. So that is what we could not get activity beyond millimolar scale, and the paper was published in tetrahedron asymmetry. And that is the end of our talk, end of my talk. And finally, I would like to thank my PhD advisor, Professor Vaidi Bhankar, and Professor Todd Lowry for my postdoc advisor. These are some group pics, and this pic was taken in MITS Madanpalli. I am thankful to the department, my department colleagues also, for their support and always whatever I am getting from them. And also I find a huge support from my colleagues to conduct this conference also. Now, thank you all. I will be happy if you have any queries. Yes, sir. Please
Yeah,
tell me.
Rashmi, good. After I listened to you after so many years, your talk.
Yes, sir.
Good.
Yeah, actually,
Actually,
due to time constraint, I had to move faster. That is the only
that's
thing.
okay. Anyway, I know about your immunosugar work. Your
Yeah.
neoglycolipids work is very interesting and difficult. I
Yes,
suppose.
yes.
Very difficult.
Actually, sir, for neoglycolipids, still standard methodologies have not been developed to find out these artificial glycolipids and protein interactions practically. So that is what people are developing right now.
Right, right. Now, I'm just
Yes.
wondering on your slide 15, you showed that you started with 1 milligram of the compound
Yes, yes.
that was provided by somebody to you, or what is it? Why 1 milligram?
Yes, sir. Actually, those compounds I am showing you, yeah, in slide number 14.
15,
These
15.
compounds were gifted by a company to Professor
Okay.
Todd Lowry. And he wanted to make a library of compound out of these compounds. Yeah.
Okay.
These intermediates were not synthesized in lab. They were gifted by a company, and he wanted to develop a series of compound as a neoglycolipids. So that is why he gave me that one. And finally, I was able to supply at least 4 neoglycolipids, 5 pentasaccharides, 1 tetrasaccharide, and 1 disaccharide.
Okay.
Yeah.
But it's difficult to get these compounds, right?
Very difficult, sir. Very difficult because I was unable to monitor TLC. That is why I used to run the reactions for 2 days, so that reaction must complete. Because taking data in intermediate was that means I am going to lose my compound if I take
Mm.
more data or more like this. So
Yeah.
after hydrogenation will definitely take place. So for other compounds, I just took LCMS. I did not go for NMR also. If
Mm.
LCMS is showing my compound peak means next I am going to the next step to incorporate that lipid moiety in that.
Mm.
Like that I did it, and that column purification of the final compound, it was very difficult to handle because I have already came 2 steps, and after that injecting the sample for small column, small iodobrite column, and I used to submit all the column fractions little bit whatever I got for first to take NMR. When
Mm.
I saw the peak, that fraction only I used to go for Maldi and LCMS.
Yeah. Yeah. That's
Yeah.
good. 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 Nice experience for you.
Yes, okay. Thank you,
Oh,
sir.
okay.
Yeah.
Thank you. Bye. Bye.
Yeah. Thank you. Thank you for your kind attention, sir. You were
Yeah. Yeah.
doing all the talks from the morning time.
Yeah. Actually, they were all good talks. Very nice. Good.
Yeah. Yes,
Yeah.
thank you, sir.
You.
So if there is no more questions, we are about to close this session right now.